Let's discuss end correction in organ pipes. When we talk about organ pipes, we know well that in organ pipes, if some air or a gas is filled, longitudinal waves can exist. And say when a vibrating tuning fork or any oscillating source is brought close to the organ pipe, longitudinal wave propagates from the other end, these are reflected, comes back. And even if the source is removed, we can say the medium particle will oscillate up and down here. As in longitudinal waves, medium particle oscillates along the propagation of waves. And within the boundaries of the organ pipe, medium particles are restricted to oscillate along the length of the pipe. But as soon as due to collisions, the wave will approach to the open end, due to continuous collision of medium particles inside the tube with the air particles or medium particles outside the tube, the particles will get scattered like this. You can see the situation here. So you can see in this situation, the medium particles, when collide with the particles outside the boundaries of the organ pipe, these will get scattered. So due to this, the air or the medium which is just outside the organ pipe, due to scattering, its density decreases. Or we can say this is the region which will become rarer, or the sound speed in this region will increase. So when the wave coming from the organ pipe penetrates the medium up to some distance, as soon as the medium density decreases, the change in medium takes place and the wave is reflected in same phase. As we have already studied, whenever a wave is reflected from a medium which is rarer or where sound speed is more, the reflection takes place in same phase with that of the incident wave. So we can say in this situation, at some distance above the organ pipe, constructive interference takes place in the incident wave and the reflected wave. So this is the point where we can say an antinode is obtained. Antinode is not obtained exactly at the open mouth of the organ pipe, because medium density decreases after penetration of some distance within the medium, and this distance we call end correction, denoted by small e, and here this end correction is written as 0.6 times the radius of organ pipe, if r is the radius of pipe. In this situation, we can say if the pipe is narrow, very easily the wave can scatter, or the medium particles can scattered by the wave. So at some smaller distance the wave is reflected, so end correction will be less. And if the pipe is broader, due to large number of particles, the wave can penetrate more into the other medium before getting reflected, so end correction will be more. Let's have a look on a situation when stationary waves are formed in organ pipes, which are one is narrow and one is broad. Here you can see there are two organ pipes given to us. One is narrow, which is of radius R1, and other is relatively broad, which is of radius R2. These are two sections which we can see here. The pipes are, you can see, these are relatively lengthier. In this situation at open end, we can see for a narrow pipe, easily the medium particles are scattered by the wave coming from organ pipe. So wave is reflected from a very small distance, that's why this end correction is low. So this is the region where antinode is actually obtained, which is slightly above the open mouth. And in case of a broader organ pipe, more number of particles are there, so wave will penetrate up to some distance before it will scatter the medium particles. So relatively you can say end correction will be more, and this is the region where antinode is obtained. So in this situation we can say if this is E1, this is E2, so E2 will be more than E1 because R2 is more than R1. This is the way how end correction is accounted in various organ pipe. Let's also have a look how end correction affects the fundamental frequencies of oscillations and higher harmonic of oscillations of organ pipes. So if we have a look on a closed organ pipe which is open at one end and closed at the other end. If it is open at one end, we can say in this situation for fundamental frequency, if its length is L, antinode is obtained slightly above the open mouth or organ pipe, and node will be obtained exactly as the closed end, at the closed end which we have discussed. So in this situation, this distance above the open mouth is E. So here we can say in a closed organ pipe, for lowest mode of oscillation, we can use here L plus E is equals to lambda by 4. For higher harmonics also, instead of length we use L plus E as lambda by 4, 3 lambda by 4 and so on. So in this situation we can write the wavelength can be written as 4 times L plus E. So here we can write the fundamental frequency to be N naught is equals to V by lambda, which can be written as 4 times L plus E. So rather than using V by 4L, now we'll use V by 4L plus E if end correction is accounted for the fundamental frequency of the open organ pipe. And for higher harmonic frequencies also, instead of L, everywhere we use L plus E. Similarly, if we talk about the open organ pipe, this is the case for closed organ pipe. In case of open pipe, at both the open ends, antinodes are obtained. So we can say for fundamental frequency, this would be the situation that on both sides the antinodes are obtained away from the open mouth of the organ pipe. Say if organ pipe is of length L on both sides, end correction E has to be accounted, and in this situation we can say in open pipe for lowest mode of oscillation we use L plus 2E is equals to lambda by 2. So here lambda will be twice of L plus 2E. So in this situation we can write fundamental frequency of oscillation should be N naught is equals to V by lambda, and lambda we should write twice of L plus 2E. Just keep it in mind whenever end correction is accounted for the case of an open organ pipe, rather than length L we have used earlier, we'll use L plus 2E now. So this is the basic difference and the effect of including end correction in case of calculation of frequencies in closed organ pipe and open organ pipe.